तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be the last lecture in this course, and I want to complete what I was saying about how electromagnetics leads us to transmission line theory, and then make a survey of what topics we have covered and what topics we have left out, which you should cover on your own. So the last lecture I had started with waves, plane waves, and talked about what happens if you take a plane wave and put it into a pipe. And further, I talked about a special kind of wave inside a pipe which still looks like a plane wave. Namely, I have some cable and I look for a wave such that the x and y variations and the z and t variations decouple. That is to say, this portion by itself is equal to 0 and this portion by itself is also equal to 0. If we could do this, then there are several benefits. One of the benefits is it's back to our 1D plane wave problem, and we have already seen that the 1D plane wave problem has solutions of the form f of z minus ct plus g of z plus ct. And this is tremendously important, because supposing I was using this in a practical circuit and I have a switch that is just closed. One lead goes to the middle, the other lead goes to the outside conductor of my cable. When this switch closed, current went from 0 to some value and then continued to evolve. So there was a jump in current. This jump of course is limited by the inductance of the system here and parasitic capacitances and things like that. Now what is received at the other end? This expression tells us what is received at the other end, because if I have a signal that looks like I of t, then what is received at the other end is I of t plus z over c, because the signal arrives later, naturally it arrives later at the destination than it left, and it must be of this form, which means that even at the destination the signal was 0 up to later time, then went up and did whatever it did. So it is the fact that we have solutions of this type that make for a very accurate transfer of signals through a cable. This is why when we buy expensive oscilloscopes, you will notice that a lot of money has to be paid for those connectors. The high quality connectors are not cheap, That is because they have to obey this kind of behavior, what is called distortion free carrying of a signal. They have to do that for very high frequencies. Even if the rise time is of the order of nanoseconds, this kind of behavior should happen. So that is why you will see that an oscilloscope has a megahertz rating. Up to that frequency, the oscilloscope can give you signals faithfully, and they will give you cables that you are supposed to use with the oscilloscope, which in fact also carry this information faithfully up to that frequency. So it is very important that we be able to get plane waves in a pipe. That is what it is. This is a plane wave, one dimensional wave, and I want to send this one dimensional wave through a pipe. The only way I can do it is if I can solve this problem. And as we saw last time, the way to solve this problem is to look for solutions of the type the electric field, which is a function of x, y, z and t, is some perpendicular function, it is a function only of x and y, into e to the power of j omega t minus kz. Of course, it can also be j omega t plus kz. Now, what do we get from this? This you can do anyway. This is just Fourier transforming in omega and k. You may not yet have learnt about networks and systems, but if you have an equation whose boundary conditions are nice and which do not have coefficients that depend on z and t, you can always go to another way of representing quantities, which is by representing them as complex exponentials. But in addition, we make one more requirement. Since we are looking for this term being 0, that amounts to saying del squared del x squared of e perp plus del squared del y squared of e perp equals 0. This is like a 2D Poisson equation, except it is an equation in e perp and not in phi. The Poisson equation you have seen is del squared phi equals 0, that is Laplace's equation. But this is Laplace's equation for electric field and not for potential. The way we get around this is, we say that if this is true, then let us calculate what taking the gradient of this equation is. So, I will get del del x along the x direction of del squared phi plus along the y direction del del y of del squared phi must also be 0, because del squared phi is 0, this must also be 0. But this del squared is nothing but second derivative in x plus second derivative in y, and this is a derivative with respect to x. So, it is always true that del del x of del squared del x squared is the same thing as del squared del x squared of del del x. These derivatives commute. Similarly, del del x of del squared del y squared can be written as del squared del x del y acting on del del y. It is a second partial derivative, they commute. So, I can write this as del squared del y del x acting on del del y. But now I take it in the other way, del del y of del squared del x del y. Do the same thing I did here, and I get del squared del y squared of del del x. So, I can push this del x right through to the inside, which means that if I take this expression, I can go from this expression to del squared of minus grad phi is equal to 0, which is nothing but this expression. So, what all this means is that if I want to solve del squared of E perp is equal to 0, all I have to do is solve Laplace's equation for potential, and I can automatically get the solution for electric field. We did this last time and obtained what is called the TEM mode. At the end of last lecture, what I did also was to proceed to the circuit formulation of transmission lines, and I want to spend a little more time there because it's a fairly subtle thing. Supposing I have a cable, and this cable is a BNC cable. So, it has an inner core and an outer shield, and let us say that the outer shield is grounded. Now, I have applied this approach to it. So, I believe that my electric field E perp is a function of x and y only. I can solve for capacitance, so this is a correct approximation. My electric field will be mostly radial, and if I want to solve for the magnetic field, well, there is a current through this central wire, so the magnetic field will be in the theta direction, and therefore E cross H, which is radial cross theta, is in the z direction. So, it is a consistent picture we have. Now, the question is, can I go from this picture to my transmission line picture, which is this picture. So, what I did last time was I said consider a point 1 and a point 2, consider another point 3 and a point 4. 1 and 2 are at the same z, call it z naught. 3 and 4 are at z1 or z naught plus delta z. So, I did an integral. I want to find the voltage here. V of z naught is integral 1 to 2 E dot dl. That is because electric field is derived from a scalar potential. V of z naught plus delta z is equal to integral 3 to 4 E dot dl. So, there are two line integrals I can do, and these two line integrals give me the voltages. But these two voltages are not the same, and I would like to know the derivative in voltage, that is del V del Z is equal to V of Z naught plus delta Z minus V of Z naught divided by delta Z as delta Z goes to 0. That is the meaning of derivative. Take the difference of voltage and divide by the difference in position and take that difference to 0. But that is equal to integral 3 to 4 E dot dl minus integral 1 to 2 E dot dl over delta Z. That is, I have to go 3, 4 and then I have to go 2, 1. And I can add these two segments because electric field anyway is radial. So, E dot dl is 0 on those two legs. So, I can write this as loop integral E dot dl over delta z. Now, I did my Stokes theorem, applied Faraday's law, and what I got was this is equal to minus del del t of surface integral B dot ds over delta z. This is just Faraday's law. Now, this B dot ds is magnetic flux through this rectangle, and the magnetic flux through this rectangle is clearly proportional to delta z. Therefore, this delta z is going to cancel out. How much flux is there? Phi magnetic is equal to L, which is the inductance per meter, times dz times I. Magnetic flux is Li, but in this case the inductance is a distributed inductance. It is not an inductance that is sitting in one point. So, the amount of inductance between z and z plus dz is L dz. So, I should write this as L delta z. So, the delta z cancels out, and what we are left with is the first equation, which is del v del z is equal to minus L del I del t. So, this is the first transmission line equation, and it comes from looking at Stokes theorem applied to this rectangle. Now, for the second equation, we have to be a little more careful. Now, what I want is to look at a loop going round the inner core, looping it in the positive sense. If I do h dot dl there, integral h dot dl is therefore equal to surface integral curl of h dot ds, Stokes theorem. So, this is curl of h on this surface. This surface is in the xy plane because it is all at z equals z naught. Let me apply Maxwell's equation here. It is equal to surface integral j dot ds plus del del t of surface integral d dot ds. Now, whatever electric field I have is in the x and y direction. There is no z electric field, which means d dot ds is 0 and integral j dot ds is current. So, it is I. If I do the same calculation at z plus delta z, again in the same direction. So, this is at z naught. At z naught plus delta z, loop integral h dot dl is again equal to I. Now, this current is current at z naught, this current is current at z naught plus delta z. Let us work here itself so that we have this equation in place. What I am going to do is I am going to make a surface out of this. I have two line integrals, but I am now going to take this surface, the surface that connects the first line integral and the second line integral. The surface integral of d dot ds, the displacement vector, now this surface is just outside the conductor, so there is no j. So this d dot ds is directly equal to charge enclosed. That is clear, because divergence d is equal to rho. So if I apply Gauss's law, that gives me that this surface encloses a certain amount of charge. How much charge does it enclose? That charge is nothing but Cv. But this capacitance and the charge enclosed clearly depends on delta z. So I can write this as C delta z times V of z. So this is the displacement vector that if I integrate it on this surface that I have showed. Note that there is no displacement vector d dot ds on this surface or on the other surface. Now what I am going to do is I am going to construct del I del z, because I already have these two results. I of z naught plus delta z minus I of z naught divided by delta z is equal to loop integral at z naught plus delta z of h dot dl minus loop integral z at z naught of h dot dl divided by delta z. That is just from these two derivations. So I am saying that this loop integral of h dot dl contains the current enclosed. But if I look at what this loop is, if I look at a ring like this and I ask what is the boundary of the surface which I have marked with horizontal lines, that surface has a boundary which corresponds to going on that edge and going on this edge in opposite senses. Because if you like, the way to think about it is, supposing I break this and make a ring that is not a loop, then the edge of the surface is going to be going round this inner surface, going radially out, coming back down, and then coming back on the return path. If I join these two parts of h dot dl will go away. Therefore, for a complete surface, this surface integral of curl of h dot ds is nothing but loop integral of h dot dl at z naught plus delta z minus loop integral h dot dl at z naught. So in other words, this piece can be written as surface integral curl of h dot ds divided by delta z. This surface is the surface I have shaded as horizontal lines. Maxwell's equation is there now. There is no conduction current, all the conduction current is inside the wire. So this must be equal to surface integral of del d del t dot ds divided by delta z. I can pull that del del t out, and you can see that I already have d dot ds is c delta z v of z. So what do we get? There is a sign problem that will be there. So let me draw the ring again. I am going to break the ring here. So I have a loop that goes this way. If I have such a loop, when I do the right hand rule, I am talking about flux entering this surface, whereas what I count by d dot ds is the flux leaving the surface. Therefore, there is a minus sign when I connect up the loop integral h dot dl and curl of h dot ds. So what I have here, h dot dl z plus delta z minus h dot dl at z is actually minus of curl of h, which is minus of del d del t dot ds. You can see this because if you go round, you have to use your right hand rule. You find that you are talking about inward pointing flux of curl of h. But inward pointing is not what we need, because d dot ds is talking about outward pointing flux of d. So what you get is therefore minus del del t of surface integral d dot ds divided by delta z. I now apply this, the delta z cancels out, so that gives me minus c del v del t. So that gives me the second equation, which is del I del z is equal to minus c del v del t. It is important to realize that we have used a lot of the ideas in TEM waves. For instance, when I did this integral, I said dz is 0. Otherwise, when I did the integral at one particular z naught and I got curl of h is equal to I could not have dropped this d dot ds. Similarly, when I do the E is equal to minus grad phi, I could not have done that unless Bz is 0. So all of these ideas have been used, but at the end of it we get two equations which are purely circuit equations, and these circuit equations are what we use when we want to talk about transmission lines. I now take the z derivative of this equation. So what do I get? Del squared v del z squared minus is equal to minus L del del z of del I del t. I can interchange z and t, so I get minus L del del t of del I del z. Apply this equation, I get minus L times minus C times del squared V del T square. So we get the final transmission line equation, which is del squared V del Z squared minus LC del squared V del T squared is equal to 0. And this is where electromagnetics is leading up to, because you can see the amount of work that is actually hiding behind such a simple equation. We are no longer talking about electric fields, we are no longer talking about magnetic fields. In fact, we say magnetic field is nothing more than current, electric field is nothing more than voltage. Yet the final equation is deceptively simple. This equation has solutions which say V is again equal to f of z minus Vt, where V is 1 over square root Lc plus G z plus T over square root Lc. And so once again, any signal sent on such a transmission line will go through without being distorted. Now of course, any real transmission line is not ideal. So where are the non-idealities of a transmission line? One non-ideality you have is that this medium, which is characterized by epsilon and mu, may be lossy. So epsilon may be complex. If epsilon is complex, we know that you will start having a leakage current. So the equivalent circuit will not just be a capacitance, there will also be a resistor in parallel to the capacitor. So you will start having a resistive current between the inner wire and the outer wire. So in place of just having capacitors, each of which has a value C over 2 dz, you will also have a shunt resistor. The second kind of loss you have is in the wall itself, because you are having currents. These currents of course are travelling on the very edge of these wires because of skin effect, and as they flow you obviously have an electric field. You have an Ez which is equal to I, or J if you like, Jz divided by sigma, where Jz is equal to Iz divided by the volume over which the current is flowing. But this is violating whatever we said about these waves. These waves have only x and y direction, but we require a z direction electric field. So it means that in a true TEM wave is not possible the moment your wire has finite conductivity. If it is a superconductor we can manage, but if it is not a superconductor then we can't have such an electric field. We must have such an electric field and we can't have it in this kind of formulation. So what happens is that we must adjust for this formulation. We must take a little bit of electric field in the z direction, most of the electric field in the x and y direction, and see how much that distorts our picture of this plane wave in a pipe. It can be done, it has been done of course, and what you get is that you must add a very small series resistor to the inductance. So you have L dz and you have a little bit of resistance. So these are called the shunt impedance is called, admittance is called G, series resistance is called R, series impedance is called L, series inductance is called L, and the capacitance is called C. These are standard symbols that are used. But this is the kind of working model equivalent circuit that describes what is actually happening inside such a cable. Once we put these circuit elements in, more or less you can throw away electromagnetics. This equivalent circuit now contains all the things we need of it. But there are some things you must bear in mind here. One of the things you must remember is that if you look at a picture like this, and if you know that the equivalent circuit is dominated by inductors and capacitors, now what I would expect is that I would have an AC voltage source, forget the switch for the moment, I have my internal ZI, and I have this transmission line. I would certainly expect that given that it's mainly inductors and capacitors, that this can best be modeled as an effective inductor or an effective capacitor, depending on whichever one is more important. At some frequencies it may look like an inductor, at some frequencies it may look like a capacitor, which would imply that the voltage across the input leads would either lead or lag the current by 90 degrees. So you expect times some impedance. You expect that either the voltage leads or the voltage lags the current. But this is not the case. In fact, if we go back to this picture, we know that the electric field, which is a function of x, y, z and t, is equal to eta times the magnetic field, where eta is nothing but square root of mu over epsilon. What that means is that wherever the electric field is, if this electric field is, says, sine omega t in dependence in time at a particular z, this magnetic field is also sine omega t. It is not cos omega t. So the signals are in phase. Inside a wave, the electric field and the magnetic field are in phase. In an inductor or a capacitor circuit, the electric field and the voltage and the current are out of phase. And this is a big difference, which means that if you use a transmission line, you will not get this. You will instead get Vi is equal to some impedance times Ii. That is, the voltage and the current will be in phase, and this transmission line will look like a resistor. And the theory of transmission lines starts with this, namely that there is a characteristic impedance to a transmission line. It is a real number, which means it looks like a resistance, and your source must drive this characteristic impedance of the transmission line. This is a very fundamental difference from circuit theory. In circuit theory, when we see inductors and capacitors, we expect immediately that voltage leads or voltage lags the current. That is not what you should expect from a transmission line. Why is this difference there? The best way of looking at a transmission line or any wave going through a pipe, a waveguide, is that you should think of this lead connecting to the leads of the transmission line. You should consider this part as an antenna. You are delivering radiation into this pipe, and you know that when we discussed what happens in an antenna, there is energy going away. whatever energy is coming is going through this transmission line and eventually landing up in a load far away. And therefore, if energy is leaving us, there is only one way energy can leave. If there is voltage and current in phase. If voltage and current are exactly out of phase, what it means is that there won't be any real power delivered at all. It will all be reactive power. But I am delivering power through a transmission line. If I send a spike, that spike goes to the from my computer to the next computer and vanishes, which means energy went from where I sent it to where it's needed. If energy must be sent, I cannot have a reactive network. I must have a resistive network. So this Z0 must be thought of as a kind of a radiation resistance of my transmission line. Typical numbers of Z0 are 50 to 100 ohms. A BNC cable has 50 ohms. A twisted pair telephone cable has 100 ohms. So this is the range of numbers that you will see. The rest of this theory properly belongs to a transmission lines course, and I don't want to go further into it. What I want to establish is this picture of being able to model a transmission line by inductors and capacitors actually has behind it the entire theory that we have studied this course, during this course. It contains electrostatics in order to establish the electric field. It contains Gauss's law in order to calculate the connection between the electric flux and the charge enclosed. It contains Ampere's law in its original static form when you want to link up loop integral H dot dl to current enclosed. It involves the Faraday's law when you wanted to calculate the first of the two transmission line equations, and it involved the generalized Ampere's law when you wanted to calculate the second equation, which got us here. So all of electromagnetic theory got used in this simple derivation that got us from fields inside a pipe to circuit equations. It's all there, and in a certain sense, if you can understand how we went from a cable to these equations, you have more or less understood all that I wanted to teach you in this course. Okay. So that more or less brings us to an end of this course. I want to discuss for a few minutes what are the topics that I should have covered which I haven't, which you would benefit from reading further on your own. So let us just put down what we have covered and see what holes are left. As far as electrostatics is concerned, we adequately covered the first part, which is to establish that the electric field is coming out of charges. So 1 over 4 pi epsilon naught volume integral rho of r prime r minus r prime cubed into r minus r prime. And we got from it that the electric field is equal to minus grad phi, and that divergence of D is equal to rho. At the end of this section, we derived Poisson's equation. Now we didn't spend nearly enough time on this equation. I just gave 1 or 2 examples where I solved this problem, this equation, and worked out cases of capacitance with multiple dielectrics, and one case where I had a cylindrical cavity and used this equation to solve for potential. This is one area where I strongly urge you to go back to the textbook and look more carefully at the solutions that you can get. Some more points inside this area are the uniqueness theorem. These are formal theorems, so I have not really covered them, because I don't think that I would do anything better than what the textbook does already. But they are the foundations for doing the rest of electromagnetic theory. So you should certainly read up on how it is that you can show that if I get a solution for potential in a region, that solution is the only solution that can be got. That's a very important statement, and it's something that you should read up on your own. When we came to magnetostatics, there's one more point in electrostatics which I did not do sufficiently. I talked about capacitance and stored energy. However, I did not talk about mutual capacitance. This is perhaps not very important for power electronics and EEE in general, because it really comes up more when you are doing microelectronics, VLSI, RF boards, things like that, where what happens is that you have a capacitor, you have a device, and the device has a capacitor somewhere, and the capacitance occurs not only between, say, the junctions of your transistor, but also with the substrate. So there is something called parasitic capacitance. And it has a strong effect on the frequency response of many devices. So parasitic capacitance and mutual capacitance come from the possibility that electric flux lines don't always go from one plate to another. It's possible that you may have multiple plates. Maybe I have a plate held at voltage V1, another plate held at voltage V2, and the third plate is grounded. In that case, instead of all the flux lines going between V1 and ground, I will have some flux lines going from V2 and ground, and some flux lines perhaps going from V1 and V2. In such a system, I cannot define a single capacitance. For one thing, it's a 3-port device or 3-node device. It is not a 2-node device. So I cannot define capacitance between 2 nodes. But what I can say is, if I set V2 to 0, what is capacitance between V1 and ground? If I set V1 to 0, what is the capacitance between V2 and ground? And if you build up such pairwise capacitances, you can talk about a capacitance matrix. This is very similar to what we call the inductance matrix, which we did do in when we talked about magnetic fields. When we came to magnetostatics, a lot of the material was the same. So we defined magnetic field, we defined the vector potential. We said B is equal to curl of A because divergence of B was 0, and divergence of B was 0 because essentially B is driven by currents, electric currents. There is no such thing as magnetic charge. And then we came up with the Ampere's law. And again, discussion about materials, we generalize this to curl of H is equal to J free. Now really there wasn't enough discussion about the relationship between H and B. Whereas the relationship between D and E is rather simple. D is just epsilon E, where epsilon is a constant. The relationship between B and H is quite complex. So B is a nonlinear function of H. Not only that, it depends on the history of how H changed. So it's you have hysteresis, you have nonlinearity, you have everything inside these two equations. And most of the complications of magnetic systems comes here, and I skipped all of that. So I am hoping that those complications will be covered better in courses which you will do in connection with machines and transformers. We were not able to talk about magnetic stored energy till we introduced time dependence. So we introduced Faraday's law. And when we introduced Faraday's law, we were able to talk about stored energy in the magnetic field. Stored energy in the electric field we showed was epsilon naught E squared over 2. And if it's a material, this epsilon naught is replaced by epsilon. So we got stored magnetic energy which was B squared over 2 mu naught. As usual, if there is a material, it is B squared over 2 mu. But this expression is suspect, whereas this expression is a good expression. This one should not be trusted because it assumes that B is equal to mu H and mu is a constant. So it will work only for very simple systems. All interesting systems will fail this expression. There was one topic in here which I did not cover properly, and that had to do with current free regions where you can derive H from a magnetic scalar potential. While I mentioned this, I did not really solve any problems with it, and this again is something that you will use a lot in your machines courses, in your transformers courses. So it doesn't require that I talk much about it, but you should be aware that this comes from the fact that if curl of H is J free, and if J free is 0, then again you can derive H from a scalar potential. Once we had Faraday's law, we were able to talk about inductance, and I introduced inductance and mutual inductance, and so we talked about the inductance matrix. And I think that coverage was fairly complete. There are areas where you can do better, but again, this is a core area of EEE, so I am sure it gets done in much better detail in other courses. Once we had completed that, we came to waves. Now, waves is a very large subject, and we basically touched the minimal parts of waves. We looked at 1D waves and showed that they consisted of forward moving objects and backward moving objects. And we looked at the properties of these one dimensional waves. We got things like skin effect, we got reflection, refraction, transmission, etc. One topic I did not cover here was polarization. It's a important complication of waves, but we will not cover it in this course. In skin effect, there is an important concept which I did not cover, which needs to be covered, and so you should read up whatever your textbook says on something called surface resistivity. This is not something new. It's just saying if I have skin effect, how can I take this skin effect and talk about how resistors change their resistivity. And finally, using waves, we went to transmission lines, which is where we have been in the last few lectures. And transmission lines is something you will spend a great deal of time doing, because that is going to be your bread and butter. So I must admit that this is only a sampling of the various topics that are there in electromagnetic theory, and each of these topics could have been done in far greater detail. And what this course is supposed to have taught you is not how to become an expert in electromagnetics, but to know what topics are there so that you can yourself study them in more detail if you go into industry and you need it. So I hope you enjoyed the course, and I will meet you in future courses sometime later. Thank you.